Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Vapor Liquid Liquid Equilibrium. Till now what we have seen? We have seen a vapor phase and a liquid phase being in equilibrium. They are coexisting and they are in equilibrium. So, then how to find out their equilibrium composition, that is what we have seen. And then also we have seen a case where two partially miscible liquid systems or liquid phases are coexisting and they are at equilibrium. So, then how to find out equilibrium composition of those liquid-liquid equilibrium system, those things we have seen. But now in this particular lecture what we are going to discuss is that is it possible that a vapor phase and two partially miscible liquid phases are coexisting. So, that VLE, LLE both of them are there. In addition to that VLLE is also there, that is vapor liquid liquid equilibrium. Two liquid phases and one vapor phase are in equilibrium, they are coexisting and they are in equilibrium. So, then how to obtain their composition, equilibrium composition, that is one thing. And then other thing, important thing, that how this phase diagrams of these VLLE systems look like. VLE systems and then LLE system we have seen the phase diagram system etc., how they look like, those things we have seen. But now we have to see for this VLLE system how the phase diagram would look like. So, let us consider three phases, one vapor and two liquid phases are coexisting and in equilibrium, right. So, let us say we have a closed system as shown here in this picture. There is a vapor phase which is designated as V and there is a liquid phase designated as alpha phase. There is another liquid phase which is designated as beta. So, these three phases are coexisting and each of them are having m number of components, N1, N2, N3, Ni, Nm are the moles of those number of components N1 and from component 1 to m, and then they are given a superscript like beta, alpha, V, they indicate for different phase. Let us say N1V, N2V, N3V and so on. So, Nmv are nothing but the number of moles of each component that are present in the vapor phase at equilibrium, and then N1 alpha, N2 alpha, N3 alpha and so on. So, Nm alpha are nothing but the number of moles of each of these components that are present in liquid phase alpha. Similarly, N1 beta, N2 beta, N3 beta and so on. So, Nm beta are nothing but number of moles of these m number of components that are present in liquid beta phase. All of them are coexisting in a closed system, right, and then all of them are at equilibrium, and then the temperature of the system is T and the pressure of the system is P. So, that is what we have. So, similar like whatever system that we have taken VLE, there one liquid phase and in one vapor phase were coexisting, those calculations we have seen. So, now here one vapor phase, but two liquid phases are coexisting and they are at equilibrium. So, while doing the calculation we will be taking the generalized cases anyway, but for simplicity what we start with a binary system. We consider a binary system, a mixture of component A and B. Okay. Then consider the case where both anisotrope in VLE and LLE coexisting. So, this having isotrope is not a kind of compulsory at all, but we start with that kind of system so that it is easy to understand. Later on in the next class we will be taking a few example problems where we will be having VLE system without an isotrope, but still there will be a kind of VLE case. Later on in the next lecture what we will be doing, we will be taking a problem and then we try to draw the phase diagram. So, we realize that without any isotrope also, if there is a VLE, then also it is possible that VLLE system is possible. But for simplicity, in order to understand VLLE, we start discussing the case having LLE and then VLE, but VLE having an isotrope as well. So, this scenario corresponds to a minimum boiling isotrope where the like interactions are stronger than the unlike interactions. Why minimum boiling isotrope, that also I explain schematically in the next slide. As the system pressure decreases, components can become volatile before the upper constellate temperature is reached. So, let us have this Txy diagram, temperature versus mole fraction diagram if we have here. So, now here we can say this Tu, this upper constellate temperature is there, right. So, above this temperature only one liquid phase is existing as in LLE case. below this TU, if the temperature, system temperature is below this one, let us say T1, so then two liquid phases are coexisting, they are partially miscible and they are at equilibrium and they are coexisting. So, at this temperature, if you wanted to find out the mole fraction of a component in each of these two partially miscible systems, so then you have to draw a tie line at this temperature and then corresponding one you can find out, right. So, this XA, this greater larger mole fraction side, probably you can have one liquid phase after this envelope, you know, that liquid phase is rich in component A. So, that is usually we call it as alpha phase, and then the lower mole fraction side, whichever, you know, having XA smaller one. So, which the smaller and then out of this envelope, which wherever this single liquid phase is there. So, that is usually referred as a beta liquid phase. Okay. So, now here out of this envelope depends on the composition, not only just upper constant temperature, you can see depends on the temperature, depends on the composition, the temperature both. So, there is a possibility that there can be a kind of a single liquid phase, that liquid phase may be rich in component A, one phase, and then another phase may be rich in component B, that is possible. And then, but within this envelope we can have both the phases coexisting, that is LLE is existing, that is liquid liquid equilibrium is existing between two liquid phases, alpha phase and beta phase, or liquid phase 1 or liquid phase 2, like that, whatever you call it. But if the temperature is above this upper constant temperature, then you will have only single liquid phase. Even if the temperature is less than the upper constant temperature, there would be some region, depends on the mole fraction, depends on this XA value, there may be single phase is possible, right. That single phase, one single phase, one side lower XA side, the single phase is usually beta liquid phase, and then higher XA side is usually, you know, alpha liquid phase. That is what we have. Now, if the temperature further away above this TU temperature, upper constant temperature, let us assume there is a kind of a vapor liquid equilibrium is also there. Vaporization of a volatile component is taking place, and then there is a kind of a vapor liquid equilibrium is also taking place. So, now you can see here this VLE curve whatever shown here. So, that is having, you know, azeotropic composition at this point, just for indication as shown, right. So, it is not any exact phase diagram of any system at any pressure or at any temperature, just for understanding we are doing. We will be taking one example case also, real case where we can have such kind of system as well. So, now here we can have, you know, if you draw a kind of line here like this. So, what you can have? So, here you have the liquid beta phase, liquid phase only you are having, okay. So, but this is beta phase, and then in between you can have a kind of a vapor liquid equilibrium between vapor and then liquid beta. Here again you can have in this region again you can have a kind of a vapor liquid equilibrium, but vapor and then alpha liquid would be there. Here vapor and then beta liquid would be there in the left sides. In the right hand side, that is larger alpha, we have, you know, alpha liquid, right. And then now you can see as mole fraction increases after this point, you know, this only vapor is existing for large range of intermediate mole fraction, right. Then again vapor liquid equilibrium is there. Then after this again extreme large values of XA, we have only single liquid phase. So, these kind of systems are there. So, all these things we are doing this TXY diagram at constant pressure. So, now assume the conditions are such a way that these two are intersecting, this LLE curve and then VLE curve. VLE curve is having different behavior here. V liquid beta phase diagram up to this azeotrope, and from this point what we have, you know, V liquid alpha equilibrium curve phase diagram for that vapor, and then alpha liquid combination that we are having in the right side, right. Now, if these VLE with an azeotrope whatever we have shown that one, and then this LLE curve intersect, then what will happen, that we will see. Now, in the previous slide we were talking about minimum boiling azeotrope. Because of this reason, in order to explain this one, we have taken a minimum boiling azeotropic mixture that we have taken, because under such conditions intersection of these two phases is possible if you tune the parameters appropriately. That again we are going to see. That is the reason we have taken the case minimum boiling azeotrope, so that it is possible to have a kind of, or imagine a kind of situation where intersection of this LLE and then VLE curves can take place. Okay. So, now here at the azeotrope the temperature of the system or the boiling temperature of the mixture is less than the boiling temperature of both components A and B. So, that is the reason it is a minimum boiling azeotrope. So, for this reason in order to have the intersection of this LLE and then VLE curves, we have taken minimum boiling azeotrope case we have taken. Now, when we have intersection of these things at the same some constant pressure, what is that? Let us not worry. So, then we have like this. Again here also exactly we can see here, this intersection has taken place before this temperature of the system reaches the upper Constable temperature. The pressure is adjusted such a way that, or the pressure is low enough such a way that some of the component or whichever is the mole volatile component is there, that is vaporized, and then VLE system of the system is also taking place, right, in addition to LLE. So, before there is a LLE, obviously this we can see here at this temperature TLLE, within this envelope whatever is there, within this envelope we have LLE of the system, and then here before this, usually this we have like this kind of system, right. So, before it reaches the upper Constable temperature, vapor is reduced such a way that more volatile component is vaporized and then VLE is also started, and then that VLE behavior and then LLE behavior are coinciding with each other, so that we can have this kind of picture here, right. So, again at the temperature T less than this when the temperature is small enough, that is TLLE, then we can have a kind of a liquid-liquid behavior where two liquid phases are coexisting, right. If the temperature is large, that is TVLE, then there will be a kind of VLE is existing, right. So, now here within this region, with both depending on the composition as well as the depending on the temperature, within this region what we have? We have single liquid phase, that liquid phase we call it, let us say, beta. Similarly, here also within this envelope, this region, what we can have, depending on the temperature and then composition which is falling in this region, we can have one single phase liquid, that is alpha. Okay. And then within this envelope, as usual like in LLE we have two liquid phases coexisting, that is alpha and then beta phases. Let us say at this if this is the at this point, if you wanted to know the composition of these two coexisting liquid phases, so you can draw a tie line at the corresponding temperature and then find out. Towards the right side or the higher Xa side, what we have, alpha phase mole fraction we will be having, and then towards the lower Xa side we will be having beta phase mole fraction of that particular component. Let us say A, if you do T versus Xa, if you see here, larger Xa side, whatever this tie line is intersecting with this curve here. So, let us say this curve here if you have, so this should be your, if you do the find out the composition. So, this would be your Xa alpha, but at this TLE temperature, and then this should be your Xa beta, right. That is again at TLE temperature, because at TLLE temperature we draw a kind of a tie line. We draw a tie line and then we found the composition, right. So, let us say at this temperature, if you wanted some other temperature higher than the TLLE here, but still within the range where we can have two phases. So, then again corresponding this should be your Xa alpha and then this should be your Xa beta, Xa alpha and then this should be Xa beta. So, like this you can find out the composition, right. So, now what we can see here, at higher temperature, that is let us say TVLE. At this temperature, if you draw a tie line here, so depending on the mole fraction, if the mole fraction is smaller and then temperature at this temperature depending the mole fraction is up to this range, then we have a pure liquid phase. One liquid phase is not pure, only single liquid phase is there, that is liquid phase beta, and then after that vapor and then liquid beta phase equilibrium is there. And then after that again, if you further increase the mole fraction at the same for this same tie line at temperature TVLE, further increasing the mole fraction after this point, then you can have only pure not pure, you will be having only single vapor phase, there will not be any liquid phase. And then further if you increase mole fraction at the same temperature towards the larger this mole fraction side, so then here we have this vapor and then liquid alpha equilibrium is there. And then further if you increase the mole fraction at the same temperature, what happens? We have again one liquid phase alpha is there. So, at one single temperature, you can see depending on the composition, there is a region where only liquid beta phase is there, there is a region where there is a vapor and then liquid beta equilibrium is there, and then there is other range of mole fraction where there is only vapor phase is there, and then there is other range of mole fraction where this vapor and then liquid alpha equilibrium is there, and then there is another range of mole fraction at higher XA values. We have a only one single liquid phase, that is alpha phase. So, all these things are possible in this VLE. But at this temperature at VLLE, that we call it VLLE because here this VLE and then LLE curves are intersecting, and then we have a kind of line. We have a kind of line, not necessarily there will be line, there may be kind of more complicated things are also possible. So, at this temperature these are all these two liquid phases, whatever the two liquid phases, they are coexisting because this envelope includes the region of LLE. So, this line is with the LLE, and then this line is also includes the vapor composition again. It is also there for the vapor part also. So, it is combinedly existing this region, this particular region at this temperature VLLE. What we are having? We are having this vapor and then two liquid phases at equilibrium. And then if you draw a tie line at this temperature TVLLE, so whichever is the larger mole fraction side is there, that is the mole fraction of that component in alpha liquid phase, and then whichever is the lower XA side is there, lower side of mole fraction is there, that is the mole fraction of that particular component in the beta phase, and then whatever in between this vapor that is coinciding with the vapor line, at that point whatever the composition is there, that is the composition of that particular that is the mole fraction of that particular component in the vapor phases, and all these three are in equilibrium with each other. So, this is the case of one particular VLLE, that is one vapor and then two liquid phases are in equilibrium, right. So, this is the case where minimum boiling azeotrope is there. So, then you can easily visualize the coexisting of these three phases, one vapor and two liquid phases, but not necessarily all VLEs should be looking like this. In the next lecture, we will be taking a problem and then we will be discussing how this PXY diagram look like, and then there you will be finding that there is no azeotrope present at all. Okay. So, more complicated than these things are also possible, but for simplicity, for easy understanding, we have taken this case. Okay. So, at lower temperature TLLE, three different types of phase behavior are possible. Only liquid phase beta, that is possible at lower XA, and then only liquid phase alpha, that is present at higher XA side, and then two liquid phase in equilibrium at intermediate composition, and their composition are indicated by the tie line as I have explained here, that is there. Okay. This is all at lower temperature TLLE. Lower in the sense how much lower we cannot say, that is lower than the upper Constellation temperature, that way we can take with relative to the upper Constellation temperature, less than the upper Constellation temperature at certain location T temperature, if you see that TLLE that we are indicating. Okay. So, now the same diagram I have shown here also for easy understanding. So, at higher temperature TVLE, that is TVLE is greater than TVLLE, then what we can have? We can have only liquid beta, that is again at low Xa side, and then only liquid alpha, that is again at high Xa side, and then however as Xa increases from small Xa or lower Xa to higher Xa side, then a liquid beta and vapor phase that coexisting, that is this region, followed by only vapor phase, that is this one, and then a liquid alpha and then vapor phase, that is this region is possible, right. Before after this lower Xa range where only liquid beta phase is there, and then before that higher Xa range where only alpha liquid phase is there, in between these two regions we have three different kind of behaviors we can see. Two VLE behaviors, that is vapor and then liquid beta VLE, then only vapor, then another VLE, that is vapor and then liquid alpha VLE that we can have, okay, as already described. And then composition in two phase regions are indicated by appropriate tie lines anyway. At intermediate temperature, this TVLLE, that we call it as a kind of intermediate temperature, only liquid phase beta is present at low Xa, and then only liquid phase alpha is present at high Xa. Okay. What does it mean by? There is no region where only vapor is forming, or there is no region that where vapor and then liquid equilibrium whatever we have seen at TVLE, this one, and then vapor, liquid alpha equilibrium, and then pure and not pure, and then only vapor phase, whatever these things that we have seen at TVLE, they are not present at temperature this one TVLLE. When these three phases are coexisting, so then this will be absent for this case. Okay. So, the same picture I have drawn once again. So, however, as mole fraction Xa in between these two single phase regions, that is this beta liquid phase and then beta alpha phase, both alpha and beta liquid phases can coexist along with the vapor between these two regions as Xa increases. Okay. So, liquid beta phase is given by composition on the left side. So, this is one, and then liquid alpha phase is given by the composition to the right, that is Xa alpha here at this tie line. Let us say if you draw a tie line at TVLLE, so then we have this one. Compositions, liquid phase compositions you can find out like this. This will be alpha phase, alpha liquid phase composition, this would be beta phase liquid composition. Okay. Vapor is given by point in the center as indicated in the figure here. This Ya is the vapor phase composition. So, all these three phases, one vapor and then two liquid phases are coexisting at this TVLLE. So, thus in intermediate composition region at TVLLE, this binary system exhibits vapor, liquid, liquid equilibrium, that is one vapor phase and then two liquid phases are at equilibrium. So, more complicated VLE phase diagrams where vapor composition does not fall in between two liquids have also been observed. So, we are not going into those details as of now anyway. Figure out what the PXY phase diagram of VLE would look like, that you can try, but however next class I am going to solve a problem to draw this PXY diagram for that particular problem. So, but however you can also try think how PXY diagram may look like for a VLLE system. So, now what we see, we take an example of methanol N-hexane system. And then for this one we try to draw TXY diagram at different pressures. Okay. Anyway, temperature we are varying and in order to see, but we also change the pressure at different pressures, we try to have the system. Okay. And then if you draw, we can have a pictures like this. What we understand, the activity coefficients etc. of a liquid system are independent of the pressure, provided the pressure is in low to moderate range. That is what we already understood, right. That is what we already know. That means if you do not have very high pressure, then the LLE behavior is not affected by the pressure. That is what we can say, right. But if the temperature is lower than the upper constellate temperature and then pressure is in low to moderate range, then there will be a kind of LLE is possible. So, that LLE is shown here, which is independent of pressure. Because we are calling it like low to moderate range of pressure only, in that range only we are doing it. Okay. Now, if the pressure is very low, then what happens, whichever is the more volatile component is there out of these two, that will be vaporizing, and then there is a VLE is also possible, right. And then we know this from VLE calculations, the equilibrium compositions are functions of pressure, right. How this pressure is changing, why, that is this VLE what we have seen, Yi phi p is equals to xi gamma I Fi naught, right. This gamma I is independent of pressure, but phi I here is dependent on this also we found as function of pressure and then composition. This again the pressure term is here. So, that means the vapor composition part is not independent of the pressure. So, that means VLE phase diagram would be different if you draw at different pressures. The same TXY diagram whatever you are drawing here, if you draw at different pressures targeting the VLE behavior of the same system, so then you have the different curves, and then different curves are shown here. At the low pressure is this one, bottom one, and then 1.013 bar it is a middle one, and then the top one at 3.1 bar. Whereas the LLE behavior is independent of pressure. So, then for all the cases we are having only one particular envelope, because this LLE curve we have drawn for the case where the upper constellate temperature has not reached. For those cases we have drawn here. Okay. Okay, before reaching the upper constellate temperature, whatever the LLE behavior is there, that we have drawn, and then that is independent of the pressure. So, this figure shows VLE and LLE behavior of methanol and N-hexane at various temperature. It is exactly the same way whatever we have done the previous thing, but only thing that we are taking an example and then trying to come to that state where we have this VLLE curves, okay, directly. Previously generalized one we have taken the directly. Now, we step by step we do this VLE evaluation and LLE evaluation, and then see how we can come out to the case where we can have VLLE as well. Okay. So, two liquid phases coexist in equilibrium up to temperature of about 43 degrees centigrade. So, this is upper constellate temperature, something around 43 degrees centigrade. So, below that one we have a kind of a LLE, two liquid phases are coexisting. Since liquids are relatively incompressible, as I said, liquid phase vigacities are almost independent of pressure. Thus, LLE behavior is essentially independent of pressure. So, that we are having only one LLE, whether you draw it at 0.113 bar, or that is whether you obtain this LLE behavior at whether at 0.1133 bar or at 1.013 bar or 3.1 bar, you will be getting the same curve superimposing onto each other, because the pressure is in the low range of the pressure only, not even the moderate range. Okay. 3 less than 10 bar we can say as a kind of low range pressure in general. So, that is the reason LLE curve we are having only one curve, that is because independent of pressure. Unless the pressure is very high, so if the pressure is very high, then this non-ideality of a liquid phase is also going to be affected by the pressure. Those things we have not taken, right. Or otherwise, if you have the pressure is low for the mixture to vaporize, or otherwise if you have the case pressure is low enough for the mixture to vaporize, right. Though the temperature you maintain the low temperature, but the pressure is also if very low, then one of the component may be vaporizing, and vapor liquid equilibrium may also possible, right. So, exactly what we are doing now, we will be taking this case, that is we will be taking the case of this one and then discussing in detail. So, now we will be considering the case of low pressure where the mixture can vaporize. So, same figure once again shown here. VLV curves for the system at various pressure are also shown in this figure, that is at different pressures 0.133 bar, 1.013 bar and then 3.1 bar. Their VLE behavior is also shown. Since fugacity of species in vapor phase mixture is directly proportional to pressure, VLE curves are function of pressure, even though LLE curves are not function of pressure. So, because the vapor phase mixture because the fugacity of species is directly proportional to pressure. In the case of vapor phase, the fugacity of species is directly proportional to the pressure. That is the reason we are having different VLE curves if you change the pressure. Though it is TXY curve at TXY curve, but at different pressures P1, P2, P3 if you call it. P1 we are having this one, P2 we are having this behavior, P3 we are having this behavior. The shape wise, phase diagram shape wise they are looking similar, but composition and temperature wise they are very different from one another. Okay. Whereas LLE we are having only one curve at all the pressures, because it is independent of the pressure. We have taken the pressure is such a way that this system exhibits azeotropic behavior, because now here whether this pressure is low pressure, I mean whatever the pressure you have taken, there is azeotropic behavior, but only thing that the composition, azeotropic compositions are different each case, and then corresponding temperatures are also different each case. Okay. Why it is having? Because this methanol and hexane mixture is quite non-ideal, and also the vapor pressure of this methanol and also the vapor pressure of these two components are very much close to each other. That is the reason it is possible that azeotrope may exist, and then that we can see at all the pressures that we have considered here. Only thing that if you change the pressure, the azeotropic composition is changing, and then corresponding minimum boiling azeotropic behavior is there. So, the corresponding temperature is also changing. Okay. One case it is around 5 degrees centigrade, another case it is around 50 degrees centigrade, another case it is around 80 degrees centigrade as you increase the pressure from P1 to P2, P2 to P3. And then composition of azeotropic mixture is decreasing. For P1 case it is approximately 0.4, for P2 case is approximately 0.54, and then for P3 case it is approximately 0.6. Okay. So, the same picture is shown here again. So, at the lowest pressure, that is at this case 0.133 bar, VLE curve intersect with that of LLE, that we can see here. So, this is LLE part, and then this is the corresponding VLE at this pressure. They are intersecting now. Okay. So, at this pressure, depending on the temperature and composition, one can expect to exist only one liquid phase, two liquid phases also possible, and then two liquids and a vapor is also possible, and a vapor and a liquid, one single liquid is also possible, and an only vapor also possible. All this may be depending on the temperature and then composition, any of these may possible and they may be in equilibrium. So, now same T(xy) diagram for this methanol and N-hexane mixture is shown here at different pressures P1, P2, P3, this is I am calling P1, this is I am calling P2, this is I am calling P3. So, equilibrium state that exists can be found by first determining whether the composition of the liquid is such that one or two liquid phases exist at the chosen temperature, that is one thing you have to do, and then bubble point temperature of the one or either of the two liquid present has to be determined, because based on that one only we can say whether one liquid phase is existing or two liquid phases are existing with equilibrium, or one liquid and two vapor, or one liquid and or one vapor and two liquids are coexisting, or one vapor and one liquid are coexisting at equilibrium. All those things you can know only when you find out these things. Okay. So, especially this bubble point temperature, that will help us how to determine for a given composition which of these phases are existing. Okay. So, how to find out the bubble point temperature? For example, from experimental data or from known vapor pressures and an activity coefficient model calculations, one can determine this bubble point temperature for a given system. Then if liquid phase bubble point temperature is higher than the temperature of interest, bubble point temperature, now this is the VLE. So, let us say VLE part, if you take this part, right. So, above this one we have the vapors here, okay. Above this one we have the vapors, and then below this one we have the liquid. So, let us say if you take this one, this is at this 0.1 composition, this is the corresponding temperature where the first bubble is forming. Below that it is in the liquid phase, right. If the temperature of your interest is less than this temperature, less than this bubble point temperature, or the bubble point temperature is higher than your interest temperature. Interested temperature may be, let us say you have this 2 degrees centigrade here, right. So, within this one you can have only one liquid phase or two liquids are present. If you like if this temperature and then composition is also within 0.1, so then only one liquid phase is possible. At this temperature, if your composition is higher, so then two liquid phases are possible. At this same temperature of 2 degrees centigrade, which is lower than the bubble point temperature of liquid phase, so then all this two phases are existing, two liquid phases are existing. Further higher mole fraction, but the same temperature of 2 degrees centigrade, only one liquid phase is existing, that is possible, right. Now, if the bubble point temperature is lower, then depending on the composition, so that is again that is this is the bubble point temperature, and then our interested temperature is something here. Now, it is approximately how much? 10 degrees centigrade, earlier approximately 2 degrees centigrade. Okay. So, now bubble point temperature is approximately something like 5 degrees centigrade now here at the same composition. So, now again depending on the composition at this temperature, your temperature of interest is higher than the bubble point temperature, or bubble point temperature is lower than the temperature of your interest, then depending on the composition you can either have a pure vapor at this, if you draw like this, tie line like this. So, you can have either a vapor, in this region only vapor phase we are having, or a vapor liquid equilibrium may be there in this region, right. That is also possible, that is also possible depending on the composition. So, this at bubble point temperature we have found at this composition right. So, after this we are having only one particular because this is the bubble point temperature, and then higher temperature we are taking than the bubble point temperature. Depending on the composition, you can have a VLE behavior or a only vapor behavior, or again you can have a kind of a vapor region here again in this region. So, all this is possible depending on the composition, that only either a vapor or a vapor liquid are present, that is all possible here. Okay. So, this is how you can find out. So, let us say if your temperature of interest is equal to the bubble point temperature and composition is in the range in which two liquids are present, then we can have a kind of VLE behavior where a vapor and two coexisting liquids will be in equilibrium, where a vapor and two coexisting liquids will be in equilibrium. So, let us say this one at this particular this thing, if you see here. So, this all this liquid, this envelope, whatever this envelope is there, that is for the LLE part. So, that is there. So, that is valid for these liquids also, and then that is also this point is also common point, or this line is whatever this tie line, let us say if I draw here. So, this tie line is corresponding tie line is common for both the LLE part as well as the two VLE regions as well. Okay. So, that is the reason this line whatever is there, that we call it as a VLLE line. Okay. So, now you can see it is quite similar as whatever the TXY diagram for VLLE system that we have taken previously, but without an example. So, this is with an example we are mentioning. So, this method of calculation is used to construct the phase diagram as shown in the picture, and then this shows various phase behavior regions for methanol and N-hexane system at 0.133 bar. So, now depending on the composition and depending on the temperature, you can find out whether one liquid is existing or two liquid phases are existing, or two liquids are one vapor is existing, or one liquid and vapor is existing, all that you can find out from this phase diagram. Okay. So, this is how one can construct the phase diagram behavior. So, now how to find out the equilibrium composition of VLE. So, next part is calculation methods of equilibrium composition of VLLE problems. Okay. So, equilibrium composition of VLLE. So, this going to be straightforward mathematically as we have seen for VLE and then LLE. So, to calculate equilibrium composition in VLLE, obviously the viscosity of each species should be equal in all three phases. So, for component A, we can have FAV is equals to FA alpha is equals to FA beta. Similarly, for component B also we can have like this. Then assume two suffix Morgul's equation for the liquid phase and assume vapor phase ideal. So, these things we are taking because these equations now you are going to realize that very complicated and very difficult to solve analytically, right. There may be approximate solutions are possible, better can be done by numerical solutions, especially if the pressure is high, then one has to go for the numerical solutions. Okay. So, for simplicity, in order to write these equations, now what we have to write, what is FAV? If you take non-ideality everywhere, then FA YA Phi AP is equals to XA alpha gamma A alpha FA naught is equals to XA beta gamma A beta FA naught. This is what you should have, right. So, what is this gamma? We should know. What is this phi A? We should know, then only we can write equation. So, phi A, there are many relations are there. So, for simplicity we are taking ideal behavior, right, and then gamma A also different models are available, activity coefficient models that we have already seen. So, for simplicity we have taken two suffix Morgul's equation, which is simplest one, where gamma A is nothing but exponential of A xb by RT, where gamma A is nothing but A by RT XB square. So, that is the reason for simplicity we have taken these two. For liquid phase non-ideality we have taken 2 suffix Morgul's equation, and then for vapor phase we are not taking non-ideality at all, we are taking ideal behavior. If non-ideality is there, that similar way we have to do the calculation anyway. So, for this condition, if you write for component A, so YAP is equals to XA alpha exponential of A by RT XB alpha square, and then FA naught is nothing but PS at, because pressure is low to moderate pressure cases we are doing, and then is equals to FA beta, that is XA beta exponential of A by RT XB beta whole square, and then multiplied by PS at. FA naught is again PS at. This is for the component A, right. Similarly, for component B you can write like this. So, now how many equations are there here? So, this is one equation, and then the other one is other equation. So, 2 equations we can take independently, and then here also 2 equations independently one can take. So, 2 equations are there, 4 equations, and then we have this YA plus YB is equals to 1, and then for alpha and then beta phases XA plus XB is equals to 1, these 3 equations are there. So, total 7 equations are there, right. So, then how many unknowns are there? YA, YB, XA alpha, XB alpha, XA beta, XB beta, P and T. Out of these variables, how many of them independent variables, and then in order to find out these independent variables, what should be the degree of freedom, that you can calculate, and accordingly you can use these equations for solving the equilibrium composition, right. So, all these 8 unknowns are related by these 7 equations, 2 and 2, 4 here, and then 5, 6, 7 equations, right. Now, even for liquid equilibrium we have seen when there is no this YAP part, only this liquid equilibrium part is there. We have seen this solving this calculation is very tough, right. We have several methodologies, numerical approaches are there, they can be used to solve these problems, right. Now, these 2 relations are also in equilibrium with a vapor phase. So, YAP or YFEAP will also come into the picture if there is a non-ideality. For the time being we have not taken the non-ideality anyway here. So, then one has to write an algorithm accordingly and then solve the problem, okay, satisfying all these 3 conditions. And then we should also make sure that the trivial solutions, whatever XA alpha is equals to XA beta if you take, then all these equations are satisfying in the case of LLE, this we have seen, but that is not correct solution anyway, right. So, that you can realize if these equations are also satisfying or not. So, for simplicity what we do, we will be assuming the pressure is low. If the pressure is low, then we know this activity coefficients etc. are independent of the pressure. So, then we can segregate this problem. First we can solve the LLE part of the problem, solving only this part without worrying about what is this YAP, because now we know this part, any of these things are independent of pressure. This equation number 1 and 2, whatever this boxed one are given, whatever this boxed one are given, that is independent of the pressure. If you take the pressure is low to moderate range. So, this part you can take it as a kind of LLE part and then find out what is XA alpha and then XA beta. If XA is known, XB can be easily known, satisfying these conditions exactly the same way that we have done in previous LLE lecture. Once we have these calculations of XA alpha and XA beta, then either by taking this part or by taking the first and last term of these equations, you can solve the vapor composition part as well, where the pressure is also coming into the picture. So, that segregating we can do here in the case of VLLE. Remember, this segregating of this equation as a separate LLE problem and then VLLE problem only when the pressure is low to moderate range. If the pressure is high, we cannot do that one, and then we have to go for numerical solutions. All these 7 equations have to be solved simultaneously to obtain reliable VLE composition. Further, 4 of these equations are nonlinear in nature. Their solution by analytical methods may be very cumbersome. Obviously, we see how much nonlinear are they. For liquid systems, their activity coefficients are almost unaffected by the pressure, provided it is in the range of low to moderate pressure range. Thus, if the pressure of VLE system is in the low to moderate range, then equations of VLE system can be solved as two individual groups. First group, calculations would deal with LLE without pressure terms in their equilibrium equations, that is equation number 1 and 2, you will not be taking the first term, YAP terms you will not be taking, right. And then the remaining XA alpha plus XB alpha is equals to 1 and then XA beta plus XB beta is equals to 1 should also be maintained, that exactly the same way as LLE problems that we have solved in previous lectures. Okay. Other part of the calculation to obtain vapor composition which is in equilibrium with the two liquid phases as a separate group. Okay. We will be taking some example problems to understand how this calculation can be done in the next class anyway. So, however, this procedure of segregated calculations cannot be adopted, especially when the pressure of VLLE system is very high. Okay. This approach we can follow only the pressure when the pressure is low to moderate. References for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnit et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, Introduction to Chemical Engineering Thermodynamics by Smith et al. Okay. So, the references are for this lecture are primarily these two books, Sandler and then Koretsky. Especially the Sandler book is a very good reference book for VLLE phase diagrams as well as the calculations. Thank you.